In this example, I want to look at one more problem where we actually go through, find everything we know about the function, and then at the end sketch the graph of the function. And this time we're actually going to see something a little bit different than what we've seen up until this point. So I think it's a good problem to take a look at. So we are working with f of x equals 4 plus 2x raised to the 2/3 power. If I want to think about the domain of this function, I think sometimes writing this with the rational exponent can be a bit tricky. I'm going to just rewrite this for a second. I know that I can rewrite a rational exponent as a root. I can rewrite this as the cubed root of 4 plus 2x squared. And if I wanted to think about the domain of this function, because we're working with a cubed root, as long as the inside part is continuous, which it is continuous everywhere, it's a polynomial, then the whole thing is continuous. If this were a square root, then we might have a really big problem. But because we're working with a cubed root, the domain of this function will be negative infinity to positive infinity. It's not something that we're going to have to worry about for our problem. So that's good. One less thing to worry about. So now I can focus on finding the critical numbers. So critical numbers, I know I'm going to need to find the derivative of this function. And lucky us, we get to use the chain rule in this problem. So let's see, if I multiply by my power for the derivative, I'll have 2/3 times, inside part will stay the same, we'll have 4 plus 2x. Subtract 1 from our power, we should actually now have to the negative 1/3 power. And then for the chain rule, we need to multiply by the derivative of the inside part. The derivative of 4 plus 2x would just be times 2. So I'm just going to clean this up a little bit so that it's easier for us to work with going forward. This is really 2 over 1. So first I'm going to take 2 times 2. That's going to give me 4 in my numerator. In my denominator, I've got 3. And then I don't want to leave that negative exponent hanging around. I want to bump that down to the denominator just because I think it's going to be easier for us to work with. So I'm going to write this as 4 plus 2x to the positive 1/3 power. So I think writing those negative exponents, this is the section, this is the chapter where it really pays off because we're just not very good. We don't have a lot of experience working with negative exponents. So we're not great at thinking about how they're going to work with our problems. So I always like to rewrite them with positive exponents if I'm going to be doing anything with my derivative after this, which I'm actually going to be doing quite a bit of work with my derivative after this. So all right, we've got our derivative. My next step, what do we want to do here next? We want to think about critical numbers, which means we need to think about places where f prime is equal to 0 and places where f prime does not exist. So first, if I take my derivative and set it equal to 0, I'll have 4 over 3 times 4 plus 2x to the 1/3 power is equal to 0. Now if I multiply both sides by that denominator, I know I can't solve for x while it lives in the denominator. On the left-hand side, it's going to cancel, and then on the right-hand side, when I take 3 times 4 plus 2x to the 1/3, on that right-hand side, when I multiply that out, I'm just going to end up with 0. And on the left-hand side, everything canceled except for my numerator, so I've got 4 equals 0. Well, that doesn't make any sense. That means that we have no solutions to this equation, which means for this part, we don't have any critical numbers here. But we also need to think about places where f prime does not exist. And in this case, we do actually have something to worry about, because if I look at my derivative, I have a variable living in my denominator. And I might be worried about, well, what would happen if my denominator was equal to 0? That would make my derivative not exist. So I'm going to take that denominator, 3 times 4 plus 2x to the 1/3 power, set it equal to 0, and we'll solve for x here. So first thing I would do is divide both sides by 3, giving us 4 plus 2x to the 1/3. 0 divided by 3 is still going to be 0. If I want to get rid of that 1/3 power, what I would need to do is I'd actually need to raise each side to the reciprocal power. So I'd actually have to cube both sides. But 0 cubed is still just 0. And on the left-hand side, I've still got 4 plus 2x. So let's see, we can finish this up here. 2x is equal to -4, which means that x equals -2. So I've only got the one critical number here. I've got x equals -2 as a critical number. So let's see, what can we do with this then? We next want to use this critical number to help us find where our function is increasing, where it's decreasing, the local extrema. We want to construct our number line next. So for our number line, we'll say here is f prime. Our critical number that we found is 2. And remember, right above that critical number, I always like to write the behavior of the derivative. And in this case, we have something different happening. This is the thing that's different. Well, we found x equals 2 by thinking about where does our derivative not exist. So I'm going to put a little DNE right above that for does not exist. Sometimes our textbook will use ND for no derivative. That's fine too, but I think DNE is just a little bit more intuitive. So something weird's going to be happening there, and we'll talk about that once we get to the sketch of this function. But for right now, we're going to continue on just like we normally have. I'm going to grab my derivative just so that I don't accidentally, copy it down wrong. So here is my derivative. This is f prime of x. I want to take a number on the left-hand side of -2, plug that in, a number on the right-hand side of 2, and plug that in. So here, f prime of, let's say, -3, I'm going to work on the left-hand side first. This would be 4 over 3 times 4 plus 2 times -3 to the positive 1/3 power. And here I am going to kind of skip ahead a little bit in the computations. I end up with, it looks like, -1.058. You can check that on your own if you'd like, but I just want to kind of save a little bit of time. We're just crunching some numbers here. Decimals, fractions, it doesn't really matter. Remember, it's the sign of that number that we're after. So this tells me that f prime is negative on the left-hand side of -2. But then we need a number on the right-hand side of -2. So how about f prime of 0? So this would be 4 over 3 times 4 plus 2 times 0 to the 1/3. And if I plug 0 into my function, I should end up with 0.8399 and a positive 0.8. So that tells me that f prime is positive on that right-hand side. So if I think about what's going on there, it's decreasing and then it's increasing. I'm going to have a local minimum at x equals -2. Now notice one thing I didn't include with my number line. I did not say that we have a horizontal tangent line because we only have that horizontal tangent line at places where the derivative is equal to 0. And we didn't have any this time. Something different is going to happen. So let's see what we can say so far. We can say that our function is decreasing. Decreasing on -infinity to -2. And it is increasing on -2 to positive infinity. So that's where it's decreasing, that's where it's increasing. We also know that we have a local minimum, so we would want to know what is the y value there. So for that, we're going to have to take -2 and plug that back into our original function. So let me write that down. F of x is equal to, I believe, what do we have here? 4 plus 2x raised to the positive 2/3 power. 4 plus 2x raised to the positive 2/3 power. So I need to find the y value. I'm going to take -2, plug that into my original function. That's 4 plus 2 times -2 to the 2/3 This one works out pretty nicely. I should just have 0 to the 2/3 or just 0. So I have a local minimum at -2, 0. So here's everything I can say so far after my first derivative test. It is decreasing on -infinity to -2. It's increasing on -2 to +infinity, and I have a local minimum at -2, 0. The only thing that I have left to do then is to sketch the graph of this function. Like I said, this one's going to be a little bit weird, so stick with me here. So here's -1, here's -2. I'm going to go ahead and plot my graph right here. We have a point right here at -2, 0. And again, I'm going to make a note to myself that this is a minimum. I think that is usually pretty helpful. So I know it's a minimum, but the big difference here is I don't have that horizontal tangent line this time around. That's not going to be the behavior there. So what was happening at x equals -2? What made that so important? Well, at x equals -2, we said the derivative did not exist. And if we think way back to, what section was that? I guess 2.4. When the derivative does not exist, when f prime does not exist, we're going to have one of three things happen. We could have a discontinuity, which we could have a hole, a jump, a vertical asymptote, but we said this function is continuous on -infinity to +infinity, so it's not going to be that. We could have a sharp corner. So remember, that looks like kind of if you think about that V shape like the absolute value graph has, something like this. So that could be a possibility here. We could have a cusp, which is kind of a special case of a sharp corner, and then the next one a vertical tangent line. So that's going to look more like this. It's going to be kind of curved on either side. Or we could have a vertical tangent line, which these tend to be trickier and more difficult to spot. Those might look something like this, where here at this particular point you've got a vertical tangent line because the slope of that line is undefined. Now it can't be a vertical tangent line because if I look at that vertical tangent line, there's no way that I could make that a minimum. So it can't be a vertical tangent line. We also said earlier that it wasn't a discontinuity. In this case, it could either be a sharp corner or a cusp. With the tools that we have right now, there's actually not really a good way for us to determine which one it is. Once we get into section 4.2, we're going to talk about how we could determine which one it is. I'm going to go ahead and cheat a little bit and tell you that in this case it is going to be a cusp. So in this case, it's going to look something like this, where we have kind of a sharp corner vertical tangent line here at -2, 0. So this is what the graph looks like. So be careful when you have a situation where the derivative does not exist, because we're not always going to have that nice, smooth, horizontal tangent line. Most of the time we end up with sharp corners, vertical tangent lines, things like that. So just be on the lookout for problems like that.